All right, guys. So here on to talk about chemical bonds a little bit more. Kind of get on into section 2. Let's start back off and review this. Whoa, what happened? Review this real quick. Again, just to talk about what we talked about in the last video, and I know you can go back and watch that as many times as you need to. So we have ionic bonding. We'll start over here first. Ionic bonding is the bond between two ions, a positively charged cation and a negatively charged anion. We know there is a transfer of electron that takes place when we have ionic bonding, and then they're attracted to each other because of that opposite charge that they have. And then covalent bonding, both of these are covalent bonding. One of them is a polar covalent bond, and then one of them is a non-polar covalent bond. Both bonds and covalent bonds in molecular compounds, we have a sharing of electrons that's taking place. So here there is a transfer of electrons in ionic bonds. In covalent bonds, they are sharing electrons. Now they can either share electrons equally or unequally. So polar covalent is when they share electrons unequally, and the atom with the most electronegativity, or the higher electronegative atom, is the one that's going to have the electrons spend more time around it, and that's going to give it a partial negative charge, and then you have a partial positive charge on the one that is the least electronegative. Okay? And then in the case of non-polar covalent bonds, or purely covalent bonds, these are equal sharing of electrons. So the electron spends much time around one or the other, so you have this balanced distribution of charge, and you don't have a partial positive or partial negative. These guys, of course, they have a distribution of charge. One of them is positive, one of them is negative. Okay? These guys have a partial distribution of charge. So there's unequal distribution of charge. One of them is partially positive, one of them is partially negative, and partially positive. These guys equally sharing an electron, so it is a covalent bond in which you have no positive or negative side to it. The whole thing is neutral, right? So in all of these, let me see that. In all of these guys, once the bond is taking place, the molecule or the compound as a whole is neutral, but just because it's neutral doesn't mean it can't have a one end that's positive and the other end is negative, okay? This doesn't. These do somewhat, and then that definitely has a positive side and a negative side, okay? So just want to review that real quick before we get into what we want to talk about today. Go into a little bit more detail about these different types of bonding, and then what kind of properties does that mean for them. Okay, so to start with, we've used the term molecule for quite some time, but I don't know that we ever define molecule. So what is a molecule? A molecule is a group of atoms that is held together by covalent bonds. Sometimes we use the word molecule a little too general, and we'll refer to any compound as a molecule. But technically, a molecule is just those compounds that are held together by covalent bonds, okay? So that would be when nonmetals bond with other nonmetals, okay? So NO2 or CO2 or H2O, water, those sort of things. Those are just a few examples of molecules. Sugar is another example of a molecule, because there's nothing there but nonmetals, okay? So nothing but covalent bonds that is holding them together. All right. Now, what is a molecular compound? Molecular compound is simply a chemical compound whose simplest units are a molecule. So a molecular compound, if you take a molecular compound and you break it apart, its base units are the molecules. So if you have water, then you have a bunch of water molecules that are bound together. And if we break it apart, then we can separate those into individual water molecules. Now, if we continue to add energy, we can take that water molecule and we can break it apart, right? So that it ends up with just being the oxygen, just being the hydrogen that makes up that water molecule. But the simplest unit is a molecule. In the case of an ionic compound, it doesn't work like that. You can break it apart, and its simplest unit is an atom, not a molecule. Okay. One of the videos that I'm going to share with you that other people have done, I think it's the one that Tyler DeWitt did, if I remember correctly. He actually kind of has a visual of that, and kind of talks about that a little bit. It should be helpful if you're still not understanding what I'm saying. Okay. So when it comes to formulas, and we're not getting into formulas a little bit, but we're going to hit this just real quick as far as the molecule goes. when it comes to writing the formula for a molecular formula, there's actually two ways that we can write the formula. We can write the empirical formula, or we can write the molecular formula. So the difference between the two, the empirical formula is a formula that gives a proportion of the elements presented in the compound, but not the actual number or the arrangement of the atoms. So it just gives us the smallest ratio of parts. Okay? A molecular formula, on the other hand, doesn't just give us a ratio of parts, but it actually tells us how many we have of each in that particular compound. The atomic symbols, and that's the same, but the subscripts are going to be different. So basically, one of them is simplified, and then the other one is unsimplified. So let me show you what we mean here. Okay? So if we look at the molecular formula, it's the unsimplified one. It's the actual numbers. All right? P4O10. Okay? So that means that this compound would have 4 of these guys, 4 P's, phosphorus, and it would have 10 oxygens. Okay? So if you actually looked at that molecule, that's how many you would have of each of those. The empirical formula for that is basically just this simplified. Well, not basically, it is this simplified. If we take these guys, both of them can be divided by 2. If we divide both of them by 2, 4 divided by 2 gives me 2. 10 divided by 2 gives me 5. So the empirical formula is this reduced simplified ratio, just P2O5. Okay? So a lot of times we'll see the empirical formula, but it's not, we use the empirical formula a lot, but it's not the actual number of atoms. It's just telling us a ratio of parts. So this just simply says for every 2 of these, you have 5 of these. If we look at this, that's still true. For every 2 of these, you have 5 of these, but the number in that actual molecule will be 4 and 10. Okay? Now, occasionally, your molecular formula is the same thing as your empirical formula, because this can't be simplified. 2 hydrogen, 1 oxygen, you can't simplify 2-to-1 ratio, because there's no number that goes into both of them besides 1, and divided by 1 does nothing. Right? So this is the same as this. All right? If we look here, N2O4 can be simplified by dividing both of them by 2 to just simply NO2. So I used the NO2 as an example earlier. I was using the molecular formula. Or excuse me, I was using the empirical formula, which is just the simplified ratio of parts. For every 1 of these guys, you have 2 of these guys in the molecule. Exactly how many do you have in the molecule? You have 2 and 4, to be completely honest. All right? And then you can kind of go on and see the rest of those. Some of them can be simplified, some of them don't. You see down here at the bottom, you've got sugar. And that's why people get confused, because there's actually a couple different formulas for sugar. Because sometimes in biology you would use the molecular, sometimes you would use the empirical, but it's the same thing. And there is more than one type of sugar. But anyhow, covalent bonds. All right, so getting into covalent bonds and the bond energy. Remember, we said that anytime 2 atoms bond together, it would be to lower their potential energy and to become more stable. So this gets us into talking a little bit about what is that energy? What is the energy of the bond? So the energy of the bond, we'll start down here for a second, is actually the energy, they describe it as the energy required to break the chemical bond and turn it back into 2 separate atoms. So if we have 2 atoms bonded together, then the energy of that bond, which is similar to the strength of that bond, right, is how much energy it takes to break it back apart and make them 2 separate atoms like they once were. So once 2 separate atoms, they bonded together. How much energy does it take to break them back apart? We refer to that as the bond energy. As it turns out, the amount of energy it takes to break them back apart is the amount of energy that they lost by getting together. Okay? So however much they lowered their energy by bonding together, because remember, if they're going to bond together, it's to lower their potential energy and to become more stable. So they chose to get together because it lowered their potential energy, right? However much it lowered their energy, that's how much we would have to raise their energy by, heat or electricity or, producing some form of energy there, right? To raise that energy enough that they decide, okay, we're going to break apart. We can't stay together anymore. Okay? So, bond length. To come back up here, bond length. What is bond length? With covalent bonds, and this is just covalent bonds, because it's not ionic bonds. We'll talk about them in a second. With covalent bonds, that is sharing of electrons, right? Then the bond length is the distance between the 2 atoms that are bonded together at their minimal potential energy. That is the average distance between the 2 bonded atoms. So when 2 atoms bond together, however far those two atoms are apart, when they are at their lowest energy possible, their minimum potential energy, that is their bond length. It's not the same for all atoms, okay? You can look in your textbook in section 2 and you can look at a little chart and they'll kind of show you like a couple of different examples, hydrogen bonded with oxygen, hydrogen bonded with fluorine, hydrogen bonded with chlorine, and what those different bond lengths and bond energies are, okay? So it depends on what atoms you're working with as to what the bond energy and the bond length is going to be, okay? So these two things are related together. There is this picture in your textbooks that I pulled out and put on this slide because it does an excellent job of kind of showing you what I'm talking about as we kind of gives us good visual as we go through this, okay? So the first thing you need to understand as you're looking at this is I don't know why, but it's backwards, okay? So we start over there at A, we start on the right, and we read backwards to the left, okay? So if I can come over here, here at A, we have two separate atoms that are not together, okay? They're floating around, they're not together, and then at some point, they get close enough to each other that they feel the attraction. They say, hey, you got some electrons that I think I want. Hey, you got some electrons I think I want. And they kind of figure out the arrangement and they sort it out and say, hey, if I give one of mine to you and you give one of yours to me, we will both have 8. So they decide to share 2 electrons or share 4 electrons or whatever. Remember, they always share it in a pair. Okay? So as they get closer together, they get close enough to see to feel this interaction. And when they feel this interaction, there's always 2 forces that are taking place. Okay? You have a force of attraction, opposites attract, and then you have a force of repulsion, right? Sames repel. So as the 2 nuclei, they would be repelling each other, right? And the electrons from one and the electrons of the other would be repelling each other, but at the same time, you have the nuclei of this first atom is attracted to you have the nuclei of this first atom that is attracted to the electrons of the second one, and vice versa. The electrons, the nuclei of this one is attracted to the electrons of that. So you have these 2 forces: attraction, which is wanting to pull them together; repulsion is wanting to push them apart. Right. So right now they get close enough together to feel each other. That they're not far enough apart to really be repelling each other. So the force of attraction is winning, and as the force of attraction is winning, they get closer together. And that getting closer together lowers their potential energy. So this is a potential energy starting at 0 up here, going down because we're talking about lowering their potential energy, right? This is the distance that they are apart. So as they move closer together, that is, move back towards 0 here distance-wise, right? They begin to lower their potential energy. At some point, they get to the perfect distance from each other, okay? So that perfect distance is where the force of attraction and the force of repulsion is balanced out, okay? So attractive forces is what's brought them together, but the closer they get, that repulsive force gets stronger and stronger and stronger, wanting to push them apart, right? So when they get that perfect distance, it's where those 2 forces are both okay. They've balanced each other out. For them to get any closer together, I don't know if you can tell, but that one's a little closer than that one. For them to get any closer together, the forces of repulsion would be very unhappy and would really, really be pushing apart, and that increases their energy very drastically. Kind of a slow decline and then a very drastic increase if they were to get any closer together. So if they were trying to get closer together, they're like, they're good, this is perfect. If they get closer together, they're going to immediately, like you're trying to push 2 magnets closer than they want to be. We have 2, negative side of a magnet, negative side of a magnet, they're perfectly fine here, and they get here, they're fine. But if you try to push them any closer than that, you have a hard time shoving them together because of those repulsive forces. Same thing's going on here. They're completely content here. Any closer than that, there's a spike in energy. Okay? So this amount of energy that they have lost, that they've decreased, by getting into this bond, getting to this perfect distance. Now, by the way, they just automatically do this. They just automatically find out what works best for them, how close they can be to each other. They're going to get as close as they can because the force of attraction is going to automatically do that, but not too close the force of repulsion is automatically going to handle that too. Okay? So whatever this distance is, whatever this amount of energy is that they lost to get to this perfect distance, that is the bond energy. In other words, that's the amount of energy we would have to put in that system to break them back apart. So if we tried to push the atoms closer together, once they got back here, now they're going to bust back apart because now they've reached that amount of energy, right? Or, you know, via heat, electricity, whatever, light waves, whatever we want to hit this with to add energy. If we add this much energy, in this case, 436 kilojoules per mole, then the bonds will break back apart. Okay, so that is the bond energy for these two particular atoms. Okay, the bond length is the length. Remember, we're further apart here, going back towards zero, closer together. So according to this, for these two atoms, the bond length would be 75, and I think that's, yeah, picometers, which is really small. Okay, so how far is one nuclei from the other? This bond length, in this case, is 75 picometers. If they were to get closer together, then the bond length would be shorter, but it would drastically increase the energy. Right? If they were to get further apart, the bond length would be longer, but there would be higher energy. So we want to be as low as possible. They want to be sitting down here, and that's kind of what they automatically do. And then when we do things to them, add energy, we cause them to kind of go back up here, and that's how we can break bonds apart and that kind of stuff. Okay? So this, I don't really go on that. It was just me kind of explaining the words briefly, what it said here. And once again, this is in your textbook. So you can take that out and look at it, read the part around it, read the little figure 19, I do believe. If you'll read the information next to figure 19, it kind of explains it. Okay? So that is covalent bonds. That's when there's a sharing of electrons. So the sharing of electrons, bond length, bond energy, kind of got an understanding of what those two things are. Okay? Ionic bonding is different. Ionic bonding, you have positively charged ions and you have negatively charged ions. They've got close enough together where they, the one with the greater electron affinity, the one that is non-metal, it's on the right of the periodic table, has saw an electron, it wants that electron. The metal, the cation, what ends up being the cation, has a low ionization energy, so it easily gives up that electron and takes it on for itself, or it gives it up, and the anion takes that electron on for itself. Now you have a positively charged and negatively charged ion, and then they're bonding together, right? So they're bonded because of that difference in charge, right? Most ionic compounds exist as these crystalline solids, as you can kind of see here. Let me see if this is in the way. I don't know if it is or not. Okay. All right. So this crystalline solid here. So if you can see this kind of three-dimensional kind of grid going on here, if you can imagine all of these big dots as being an anion, if we want to talk about sodium chloride, we can call those the chlorine ions. And then these red dots, we'll say those are the sodium cations. Okay. So if you can look anywhere you look, that it just basically is it alternates, okay? So you've got, a positive, right? And in between there's a negative. Maybe I should have said the red ones were negative and green ones are positive. That's what you're probably thinking. Yeah, whatever. We'll go with it. All right? So if you look here, this positively charged ion here is completely surrounded by negatively charged ions, right? Because that's what it's going to want. A negative is not going to want to be near another negative. And if we had like another sheet in front of that, out in front of this red dot would be a green dot. Behind this red dot would be a green dot. And then that grid, that pattern just continues sheet after sheet after sheet, or layer after layer in any direction. This direction, or this direction, the length, the width, and the height of it. So you end up with this grid of positively charged and negatively charged ions, so that any positively charged ion is completely surrounded by just the negatively charged, and any negatively charged is completely surrounded by positively charged, because of course that's what they're going to that's the way they're automatically going to arrange themselves to be at the lowest energy possible. To have a negative sitting next to another negative, they would not, that's a tense. That's going to add tension, and they're going to want to push apart from each other. But a positive sitting next to a negative, oh, they're completely fine with that, right? They want that. They're good there. Okay? So that's what we refer to as a crystalline solid. In an ionic crystal, ions minimize the potential energy by combining in an orderly arrangement known as a crystalline lattice. So here's the lattice structure that makes a crystalline solid. Okay, that makes a crystalline solid. So if you look at you get a ionic compound under a microscope, you're going to see this crystalline solid. Think like a crystal, or a ruby, a diamond, or something like that. So even if you look at salt, like a salt crystal, right? And it's not that molecular compounds can't also be crystalline, like sugar also looks a lot like a salt does to the naked eye. So we're not saying that all ionic compounds are the only ones that are crystalline solids. We're just saying that most ionic compounds are crystalline solids. Does that make sense? And they have this lattice structure in place here. Okay. Let's see. The lattice energy is similar to bond energy, but we refer to with ionic compound, we refer to it as lattice energy because of the crystalline solid is that lattice. That crystal lattice structure that we talked about here. Okay, so that's where we get the term lattice energy. Lattice energy is the energy released when a mole of ionic crystalline compound is formed from the gaseous ions. So it's about, once again, it's about when the compound is made, when they get in this lattice structure, how much energy was released? How much did they lower their energy by getting in that structure? However much energy they lowered by getting in that structure, that is the lattice energy. That would also be the amount of energy necessary to break that structure apart, if that makes sense. Okay? So, however, they're going to lower their energy by getting in the structure. If we were wanting to break that apart, we would have to put that much energy into the system in order to undo that and break them apart into their separate ions again. Okay? Lattice energy is used to compare bond strength in ionic compounds. The more energy released to become the compound, the stronger it is. So if you had a crystalline solid that was made, and in doing so, it was able to release 200 kilojoules per mole, and then you have another one that, in order for it to get in that crystalline lattice structure, it was able to release 400 kilojoules. Well, the one that released 400 kilojoules is going to it's stronger, is bound together stronger because it released 400, the other one released 200. So it takes less energy to make this one fall apart as it does this one, right? The one that released the more energy is held together stronger. It takes more energy to get it to break apart. So we can talk about these lattice energies in terms of bond strength. How strong are they bound together? Okay, one ion to the next. So a little bit about ionic versus molecular. And now this is the one in the first packet that y'all did, the one that we did. Let me see if I can find it real quick. This little ionic covalent compound worksheet that y'all did. This, and in large part, this was talking about this. How do they compare? What's the differences between those two things? So, ionic compounds versus molecular compounds. One of the big things that we talk about is they're going to have different properties, right? And that's why this is important. Because if you're wondering, why does it matter if something is an ionic compound or if it's a molecular compound? It's a way of we like to classify things. It's a way of grouping things. So when we group it as an ionic compound, that tells us about what it's made of and what kind of properties it's going to have in terms of its hardness, melting points, boiling points, things like that. Even getting into the structure of how it's bonded together. Okay, so classifying it helps us to kind of learn a little bit about it just right from the get-go, knowing what group it's in, okay? So, start with, the forces that hold ionic compounds together is much stronger than the forces that hold molecular compounds together, okay? And remember, molecular compounds are covalently bonded atoms, okay? So, molecular compounds, you got to think covalent bonds, all right? Now, the forces, this part would be kind of tricky for folks. The forces that hold ionic compounds together. What holds one ionic compound to another ionic compound? It's an ionic compound. If you have one ionic compound, then it's held together just by these opposite charges. Okay, a positive with a negative, a positive with a negative. This crystal lattice kind of structure. Okay, so what holds ionic compounds together is ionic bonding. Okay, now when it's talking about the forces that hold together molecular compounds, it's not talking about the covalent bonds that is inside of molecular compounds, okay? That's holding the molecule together itself. What's holding one molecule to another molecule, right? What's holding those together, those molecules from one molecule to another molecule, is not the same thing as the stuff that's holding inside the molecule. We'll talk about the difference between those two, the inter and intramolecular, in the next video, I think. Okay, so it's not actually talking about covalent bonds here. Okay, even though molecular compounds are made from covalent bonds, this is not talking about. So this is not saying ionic bonds are stronger than covalent bonds. Ionic bonds can be very strong, but molecular bonds can also be very strong. Okay, so both ionic and covalent bonds can both be strong and weaker. So that's not what this is talking about. This is saying the stuff holding ionic bonds together, holding one ion to another ion, is stronger than the stuff that's holding one molecule to another molecule, which we refer to that as intermolecular forces. Okay? The difference in these bond strength explains the differences in properties of molecular and ionic compounds. So when we look at ionic compounds and we see their set of properties, and we look at molecular compounds and we see their set of properties, we begin to see a trend develop between those two, and that trend can be explained by the strength of the stuff that's holding it together. Okay? The strength of the stuff that's holding it together. All right? Properties such as the melting point, boiling point, hardness, and it goes on and on and on and on, is based on the strength of the bonds. All right? The Professor Dave video that I shared with you guys, he does a good job of explaining and kind of giving you some visuals to kind of see what we mean by how the melting points and boiling points are different based on what type of atom it is. Okay, and I'll show you. I'll do a little demo in just a second to kind of help with that as well. Okay, ionic compounds in general, ionic compounds tend to have higher boiling points. They tend to have higher melting points than do molecules. Okay, than do molecular compounds. The worksheet that you did in the last packet that I just showed you a second ago, that's what you read. That's what you found out in there. Is these things and a couple more. Okay, ionic compounds are hard. This is interesting. Ionic compounds are hard, but they are brittle because of their lattice structure. So if you take an ionic compound, if we had like a huge salt block here, right, which is an ionic compound, right. And what we was to take that, is hard, it would be dense, it would be heavy, right? But you could take that ionic compound with a hammer, right? And you could hit it, and when you hit it, it would bust apart fairly easily. So it's brittle. Something can be hard and brittle at the same time. Okay, you can think peanut brittle, for instance. Okay, it's in the name, brittle. Yeah. Anyhow, ionic compounds, they're hard, but they're brittle. Why are they hard but brittle? If we go back and we talk about this, if you remember that crystal lattice structure of ionic compounds, where every positive is surrounded by negatives and every negative is surrounded by positive, right? And that's a strong network they got going on, right? But because of that, if I hit that with a hammer and I cause that thing to slide so that this negative here is no longer next to a positive, but it's slid and it's next to another negative, well, of course, that wouldn't happen. Let me see. All right, so we're just looking at these two right here. Every positive is next to a negative, right? So if I come along and I hit this with a hammer, and bam, here's my giant hammer. How about that? Yeah, that's a hammer handle. Yeah, like it. Okay? And I hit that, and that shifts all of these guys down one. What's going to happen when all of these guys shift down one is this is then going to be here. And this one's going to be here. Oops. Is going to be here. And then this one would be here. Okay? Likewise, this guy would be moved here. This guy would be moved here. So all of a sudden you would have a green next to a green, a red next to a red, a green next to a green, a red next to a... So all of those like charges are now next to each one. They're obviously going to repel from one another. And when they repel from one another, that repulsion is going to cause it to break apart. So even though it's a hard substance, it's easy to hit it, make it shift, break apart. That causes it to be, to fall apart. And that's what we call stuff that's brittle. Brittle stuff is hard, but it can fall apart fairly easily, right? With a little bit of pressure. Okay? Now, last thing we're going to talk about is metallic bonding. Metallic bonding, we're not going to talk a lot about it, but just to kind of let you know that, hey, it's there. So, metallic bonding is a special type of bonding that results from the attraction between metal cations and a sea of electrons. Okay? New term, sea of electrons. So what you have with metallic bonding, so you have these metals that want to become cations. They would really like to lose their valence electrons and become more stable, right? So what they do is they all just kind of lose their electrons to each other. It's kind of a weird kind of situation, right? But it makes for some very unique characteristics, okay? So they end up sharing electrons with each other. You end up with this sea of electrons, okay? So look down here. What is a sea of electron? A sea of electron is the accumulation of electrons released by the metal cations in the bond. So you have all these copper cations that have all released electrons, and these electrons are kind of free to move from one ion to the next ion. Okay? And that freedom of movement is what makes metals metals, what makes them special, what makes them unique. Okay? So what they end up with is they have a vacant p and d orbitals in the metal's outer energy levels. And these outer p and d orbitals from this guy and this guy and this guy and this guy, they're all kind of overlapping each other. So the p and the d orbitals of that outer energy level are kind of from one atom is overlapping with another atom, right? And the electrons just kind of move from one orbital to the next orbital to the next orbital, not just in its own for that one atom, but even to the orbitals in another atom, okay, or another ion, I should say, okay? So you end up with these electrons that are kind of freely moving from one to the other, right? So the valence electrons no longer are bound to an atom, or there's not an atom that say, hey, that's my electrons, because the electrons move, they leave. And that's why we refer to it as an ion, because this guy's two valence electrons is not hanging around it's kind of moving wherever, but at the same time, others are coming in from other atoms, all right? So you have this free movement of electrons throughout this, this group of metal, all right? So it's weird, it's unique, it's metallic bonding, okay? So if you kind of look at this picture over here, so you have all these cations, right? Metals are going to be cations, and then you have all these negatively charged electrons, and you can see they're just kind of freely going just kind of wherever, right? They're just kind of free to go from this guy to this guy. Oops. All right? They're just kind of free to go from one guy to the next. All right? So what's unique about that is, like we said a while ago, metals are metals because they are good conductors of heat and electricity. That's why we classify, that's how we define a metal, as a good conductor of heat and electricity, right? So what makes it a good conductor of heat and electricity? So when we have something like this, right, and we take electricity, for instance, we could use heat, we'll take electricity, and we hook electricity up to that metal. It's a good conductor. It means that it allows the current to flow through it. If something is a poor conductor of heat and electricity, it means it doesn't allow the energy to flow through it, right? Metals have this special ability to allow the energy to flow through it because these electrons are free to move from one end to the other. Okay? So, you know, when you take and you put this, you hook this end of the metal up to the current, to the electricity, that electricity is able to kind of flow through like on the backs of the electrons, so to speak, from one end to the other. So there's this free flowing, this free movement of electrons means that energy is able to freely pass. That is heat energy, that is electrical energy, is able to freely pass through the metal. So it's a good conductor of heat and electricity. What it also means, there's a couple other characteristics of metals that are interesting, that they are malleable, and ductile, which is like the exact opposite of being brittle. We talk about ionic compounds, they're hard but brittle. Metals are hard, but they're not brittle. Or most of them not. They are malleable and they're ductile. Means that we can turn them and shape them and mold them, right? So ionic compounds, going back here, if we hit it with a hammer, it shifts down and it causes it to break because you now have the same negatives next to negatives and positives next to positives, right? On the other hand, with metallic bonding, when we hit it, it's able to kind of shift and move. However, it doesn't matter, right? We can hit the metal and it just kind of bends, it reforms. Or we can stretch it out to a string and it's able to reshape itself without breaking any bonds because of the free movement of the electrons. It just moves and molds and flows without actually breaking. It takes a lot more energy to actually get it to break, right? Because it's got so much freedom to move. Ionic compounds are much easier to break, much more brittle because it's rigid, okay? Metals are hard, but they're not rigid. These guys, ionic compounds, are hard and rigid, okay? So there's a quick little, little video just talking about the differences between the three types of bondings. You got covalent bondings, which makes molecular compounds, ionic bonding, which makes ionic compounds, right? And then you have metallic bonding, which there's just a little bit in the textbook about metallic bonding. We're just talking about just real quick, just so you are kind of familiar with it. And it's pretty much all we're going to say about metallic bonding. Okay? So, I got one more video I'm going to do on the rest of this unit without the Lewis structures, on intermolecular forces. And then after that, we'll do we'll learn about the Lewis structures after the intermolecular forces. Okay?